Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on EMC consideration. Okay, so for this video, I'm going to concentrate on field uniformity. Okay, so basically this video, I'm going to describe the step-by-step procedure to execute this field uniformity. I'm also going to discuss why we need to do this field uniformity before we actually can do this radiate immunity test. So basically, for field uniformity, okay, we need to correlate them to this standard, which is IEC EN 61000-4-3. Okay, so basically, this will be the objective of this video. This will be the part 65 series discussion on EMC. So guys, if you're keen to know more about EMC, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on EMC. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me through the comment. Okay, before I continue, okay, I'd like to urge you guys to help this channel by press the like button. Help me guys, press the like button now. Okay, it's free and it only take a few seconds. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand what is actually field uniformity. Okay, so this field uniformity measurement actually as per the IEC EN 61000-4-3 standard, they are mainly used to validate test site for radiate immunity measurement. Okay, so before you actually can do this radiate immunity, you actually need to ensure that the field will be in a uniformity. Okay, so therefore we need to perform this field uniformity test before we can actually perform the RI. Okay, so the objective of the test, okay, so actually is the field uniformity test, is to ensure that the test area, okay, usually inside a adequate or semi-adequate chamber, okay, we need to have a constant and we need to have a uniform electromagnetic wave. Okay, so this actually guarantee that the device under test actually experience the same field strength across its surface. So in short, okay, we need to ensure that all the test area that we're going to put our DUT, okay, we need to ensure that they are consistent and they need to have this uniform electromagnetic field strength so as to ensure that the DUT will experience the same field strength across its surface. Okay, the field deviation observed at more than 75% of the test point must be within the 0 dB to 6 dB limits as specified in IEC 61000-4-3. Okay, so this will ensure accurate and repeatable test result. Okay, calibration should be performed on an annually basis or any time change are made to the equipment or the test area. So in short, okay, when we actually want to do this field uniformity, okay, we need to ensure that we need to do it at least once a year. Okay, or if not, anything change. For example, when I actually change my signal generator or when I change my antenna, okay, so hence I still need to perform this field uniformity. Okay, so in this table here, you can see that there are actually 5 different level: level 1, level 2, level 3, level 4, and level X. Okay, so basically at different level, you actually has different test field strength. Okay, so from here you can see that I actually has 1 volt per meter, 3 volt per meter. Okay, so basically 3 volt per meter is mainly used for household. We also have 10 volt per meter. Okay, so basically this will be used, for example, in an industry area. Any product that actually so-called will be installed in the industry will subject to test it under this 10 volt per meter. Okay, so at some case, for example, automotive. Okay, so basically we need to test it at 30 volt per meter. And under this special category X, okay, which we call special. So X is actually an open test level, and the associated field strength may be any other value. Okay, so this level may be given in the product standard. So in short, you can see that typically most common will be 3 volt per meter and 10 volt per meter. So 3 volt used in the household, 10 volt used in the industry. So for example, some special case, okay, as per the product standard, you actually call for the different test level as it illustrate over here. There are actually two types of uniform field area. Okay, so uniform field area calibration that can be performed. Okay, one is called the constant power. Okay, so this video we are not going to concentrate on constant power, but we are going to concentrate on constant field strength. Okay, so in short, this is actually a more popular method to do this field uniformity, which is ensure constant field strength. Okay, so the constant power actually refers to maintaining a fixed rate of energy transfer over time. Okay, which means that the energy transfer will be fixed. Okay, so regardless of the time, all the energy will be so-called fixed. Okay, power is the rate at which energy is supplied, consumed, or transferred in a system. Okay, so basically this is under the constant power. Okay, like I mentioned earlier on, we are going to concentrate on this constant field strength. Okay, so constant field strength refers to maintaining a fixed intensity of an EH or electromagnetic field across space or time. In short, okay, we need to ensure, for example, the signal strength or electromagnetic signal wave, okay, at volt per meter. We need to ensure a constant field strength. Okay, so the field strength measure the magnitude of a field at a specific point in space. So basically, this is what we are going to concentrate for this video, which is the constant field strength method. Okay, let's go into step-by-step procedure. Okay, when we actually need to do this radiate immunity, before we can actually do this radiate immunity test, we need to do this field uniformity. Okay, let's understand step by step how can we actually perform this field uniformity. Okay, step number one, okay, we need to prepare the test environment. Okay, as I mentioned earlier on, we need to have a chamber. Okay, we can have either use this adequate chamber or semi-adequate chamber. So why we want to use chamber is firstly, we want to avoid reflection. Okay, so once we use a chamber, okay, we can actually minimize the reflection by putting the, for example, ferrite tiles or the absorber, okay, to prevent reflection. And the chamber also can prevent any external interference to upset our result. Okay, so therefore, in short, the chamber actually contain the environment. They don't allow any external signal enter into the chamber. Next, okay, so when we actually do this field uniformity, please ensure that you actually remove the table. When we do the RI, we need the table inside. But when we actually do this field uniformity, we need to remove away the table. Okay, so keep this in mind. Okay, so these are the equipment that we need in order to do this field uniformity. First will be signal generator. Okay, as the name implies, okay, they actually generate a signal. Okay, so basically, in short, they generate the desired radio frequency signal. So basically, they generate a signal. Next, the signal will pass to amplifier. Okay, so the role of amplifier is to boost or amplify the signal to the required test level. So basically, this generated signal amplifier boosts the signal big enough to the desired test level. Next will be antenna. Okay, antenna actually become a source that convert the signal into electromagnetic wave. So typically for antenna, we need to have a broadband antenna, and most of the time we actually will use this log periodics. Okay, basically they are used to radiate the RF field. Okay, so I think you have some idea what is actually an antenna. Okay, so basically antenna, okay, for our case, we actually broke the antenna into two types. Okay, one will be the log periodic, another one will be actually the horn. So log periodic will take care of the lower frequency. The horn antenna actually will take care of the higher frequency. Okay, so next we need to have the field probes. Okay, so the field probe is actually used to measure the intensity and also the uniformity of the electromagnetic field. Okay, so basically this field probe will allow us to measure how strong the signal is, okay, basically inside the chamber. So basically, in short, for equipment, we need to have these four. First, signal generator. Basically, after they generate a signal, they pass it to the amplifier. Amplifier will pass to the antenna. Antenna will convert the electrical signal into electromagnetic wave, and then basically they will propagate inside the chamber. Next, we have this field probe to measure how strong what will be the intensity of the electromagnetic field. Okay, so we need to ensure that we need to have a calibration. Okay, because we are doing this field uniformity, we need to ensure that all the equipment are actually cal as per the international standard. Okay, so this is actually the step number one. Okay, we actually prepare the test environment. Second, okay, before we go into second, okay, so let's quickly look at this diagram here. Okay, so this diagram is actually see how we can actually prepare the chamber. Okay, so as I mentioned early on, we have the signal generator typically will be at another chamber. Okay, so this is one chamber. We have another chamber to house the signal generator. So the signal generator generate the signal, pass it to the amplifier. The amplifier pulls up the signal large enough. After that, feed to the antenna through a cable, a long cable that link the amplifier to the antenna. So basically, the antenna will be basically convert the electrical signal into electromagnetic wave, and they actually propagate over here. So on the other side here, you can see that this is where we put our so-called field probe. Okay, the purpose of field probe is to measure how strong the electromagnetic wave. So basically, you can imagine that the electromagnetic wave actually propagate. The field probe actually measure how intensity the signal is. So basically, this give you a better idea. Okay, so let's quickly understand a few things here. So basically, remember when we actually do this field uniformity, we need to remove away the table. Typically, the table actually has a height of 0.8 meter. Okay, so this is where we start the test. Okay, we cannot do on the ground level, so we actually do a 0.8 meter above the ground. So basically, this is what we call the area that we actually will put the DUT. And basically, we have this field probe that will be measured, let's say 16 point from this so-called test site here in order to measure the field uniformity. Okay, hopefully you have a better idea what is actually field uniformity and how we can actually execute this field uniformity. Let's go to the second step. Okay, is to select the test frequency and field strength. Okay, most of the time when we actually do the RI, okay, basically the frequency range will be from 80 megahertz to 6 gigahertz. So we actually will break this into two frequency. One will be 80 megahertz to 1 gigahertz. Okay, so this is my case here. So I actually break into two band. One we call a lower band frequency, one we call a higher band frequency. So we have an antenna that actually serve from 80 megahertz to 1 gigahertz. So basically this is what we call a lower frequency. A higher frequency actually will be done by a horn antenna from 1 to 6 gigahertz. So basically, firstly, we need to select the frequency range. After we have select the frequency range, we need to know what will be the frequency step. Okay, so for example, when we actually do this 80 megahertz, we need to know what will be the next frequency to test. So typically, frequency step is 1%, which means that you can imagine I take 1.01 multiplied by 80. That will be the second test that I will do the measurement. So basically, this is the second step. Okay, we actually select the frequency range and we also decide what will be the frequency step. The smaller the number, okay, the more detailed test that you're going to do. So in short, okay, basically most of the time, typically we actually will do, like for example, a frequency step of 1%. Next, okay, we need to determine on the field strength, okay, or the field signal. Okay, so most of the time it's actually 1 volt per meter, 3 volt per meter, or 10 volt per meter. For me, okay, I will say that the popular one will be 3 volt per meter for commercial product, 10 volt per meter typically for industry product. Okay, so but most of the time, okay, in order to ensure that we actually pass the test, most of the time we actually go as high as possible. Okay, not so high. For example, if let's say we need to do 3 volt per meter, okay, we may not want to do just on 3 volt per meter because it can be quite dangerous and we may fail the test. So therefore, most of the time, for example, instead of 3 volt per meter, we will test it, let's say about 4 volt or 5 volt per meter. Same for 10 volt per meter, we will do slightly higher so as to ensure that we were able to pass the radiate immunity. Okay, so basically this is depend how stringent you are. So but the common test level are in short 1 volt per meter, 3 volt per meter, and 10 volt per meter. Okay, so basically or even higher, okay, they actually depend on the specific standard or application. So calibration is performed at a level higher than the highest test level due to the effect of modulation during testing. Okay, so don't confuse about the higher level as I mentioned earlier on. Okay, so this is totally different from what I mentioned earlier on. Okay, because we have a amplitude modulation. So therefore the calibration we need to ensure that we actually do at a level that is actually higher than the test level that we actually need. Okay, so for example, for amplitude modulation, okay, which happen at 80%, okay, the field level will reach 80% higher than the continuous wave. Okay, which means that for AM, the field level will be higher, so than our convention continuous wave. Okay, so basically what we need to do is we need to add in the 80% here, which means that I need to add in 1.8 times the field strength. For example, if let's say I want to test at 1 volt per meter, okay, with amplitude modulation, it become 1.8. Let's say it's 3, okay, so will be 1.8 multiplied by 3. Let's say it's 10, I need to do at 80 volt per meter. Okay, so let's do a very clear-cut example. Okay, for example here, if let's say we need to do this test level of 30 volt per meter, then we need to calibrate at 54 volt per meter because of amplitude modulation. How to get 54 volt per meter is basically from this equation. As I mentioned earlier on, what will be the test level multiplied by 1.8? That will be your test level that you're supposed to be calibrate at. Step number 3, okay, so we need to define the test area. Okay, typically, okay, we are going to define the area like, for example, 1.5 multiplied by 1.5 meter. Okay, or maybe some extreme case when the DUT is so huge that you need to define your test area as 3 by 3. Okay, but most of the time, okay, I think 1.5 multiplied by 1.5 meter should be enough. Okay, but for example, some extreme size of your duty, then you need to do a bigger test area 3 by 3. Okay, for my case, I actually do it in a 1.5 by 1.5 meter. Okay, so basically these are the area that you actually define where you're going to put your DUT. Okay, the uniformity of the electromagnetic field will be measured within this defined area at a specific distance. Okay, often either 1 to 3 meters away from the transmitting antenna. Okay, so basically 1 meter mainly for mil spec, 3 meter for commercial product here. So basically we put them either 1 to 3 meters away from the antenna, your DUT. Okay, either 1 meter or 3 meters away from the antenna. So you also define where will be your test area, which I'm going to illustrate a little bit more on my next slides here. Okay, so next we need to position the field probe. Okay, we need to arrange the field probe in a grid pattern in a test area. Okay, so on the next slide, I will show you this grid pattern in the test area. For example, okay, let's say we are going to do a 1.5 by 1.5 area. So we are going to place the probe at a grid point, okay, which are spaced 0.5 meter apart. Okay, so typically we have 16 points. Okay, so the probes are usually set at a height of 0.8 meter to 1.5 meter above the ground. Okay, so basically this is to mimic the position of a typical device. Okay, so I will illustrate this later on. Okay, so next we're going to set the field probe into position 1. Okay, so what does this mean here? So this is a 4 by 4, altogether 16 points. For example, let's say I denote this as a position 1. Okay, so I can also denote this as position 2, 3, 4, etc. This is not important. So basically, you need to know, okay, the position where you actually put your field probe here. Okay, so typically, if you still remember, we actually have a so-called non-conductive table with a height of 0.8 meter. So therefore, we cannot do this at the ground level. So we need to do this at a height of 0.8 meter. So basically, this is where the table where you put your DUT. So basically, this is the first viewpoint, the first so-called 4 points that you're going to measure. Okay, so basically, you can see that this test is actually 1.5 by 1.5. The point between the test point is actually 0.5, as you can see from here. Okay, so next, I'm going to do a little bit more discussion. Okay, so next will be step number 5. Okay, we need to generate the RF field. Okay, so for example, we're going to set the signal generator and amplifier to the desired frequency and power level. Okay, so nowadays the equipment, they actually do all this on their own. we don't really need to set the signal generator and amplifier. We can actually automate this part here. Okay, begin the transmitting of RF energy via the antenna to create an electromagnetic field. Okay, so basically this is what it means. So basically the key thing is to generate the RF field. Okay, so next on step number 6, okay, we measure the field strength at each point using the field probe. Okay, record the field strength at each probe location across the grid for each frequency. Okay, so these are the position of the field probe. We are going to put the field probe at this 16th position. Okay, so as he mentioned here, okay, we are going to measure what will be the field strength at each location. Okay, measurement is typically done over a minimum of 16 frequency across the selected range. So basically, this is not fixed. Okay, various situations you actually need to do various times in terms of the measurement. Okay, so before I continue, guys, again, if you have learned something from this video, okay, please consider to like and subscribe to this channel. Thank you so much. Step number 7, okay, we are going to do this analyze the field uniformity. According to the IEC 61000-4-3 standard, okay, this is often used for radiate immunity testing. Okay, the field is considered uniform, okay, if the variation in the field strength across all measured points is within 0 to 6 dB. Okay, so if you are within this 0 to 6 dB, you are so-called compliant to this IEC 61000-4-3 standard. So basically, this is what it means. So next, we need to calculate the deviation of each point from the average value of the field strength across the entire grid. Okay, don't worry. Okay, I will have an example to so-called understand this better, how we actually analyze the field uniformity. Okay, so as I mentioned earlier on, okay, when we actually do this field uniformity, there are actually two types. One is the constant power. We are not going to do this constant power. Okay, so therefore, I'm not going to discuss on this constant power, but we are going to do this constant field strength. Okay, so basically, we are going to do the constant field strength. So this is actually the flow chart for constant field strength. Okay, firstly, we set the frequency to initial value. For example, let's say, okay, at 80 megahertz. Okay, so basically I set the frequency at 80 megahertz. Okay, so next, okay, I'm going to sort each grid. So basically at one particular point, I'm going to put the field probe. Okay, I'm going to capture what will be the forward power, okay, at 80 megahertz. Okay, so after that, I'm going to collect all the 16 points. So after that, I'm going to sort all the grids point according to the descending from the highest to the lowest. So basically, this is step number 2 here. So firstly, I set all the frequency 80 megahertz. So after that, I do all the measurement. Okay, so I have all the forward power. So next, I'm going to sort the forward power for the 16 point from the highest to the lowest. So next, I will find the highest forward power. So once I have the highest forward power, I'm going to do a minus 6 dB. So once I done my minus 6 dB, okay, I will determine, okay, how many grid points are within this 6 dB. Okay, so if there are more than 75% that is within this 6 dB, my task is done. If it's not, then I need to look at the second highest, and then I need to flow this process again. Okay, but like I mentioned earlier on, don't worry. On the next slide, I will give you an example. How can we actually do this field uniformity? How can we ensure that we have this constant field strength? Okay, I think an example will be more clear. Okay, so this will be the example. So this is actually the first steps I mentioned earlier on. For example, we set the frequency at 80 megahertz. Okay, we are going to measure the 16 point. Okay, so when we actually measure the 16 point, how much forward power I need in order to achieve 10 volt per meter, for example, for this case here. Okay, so basically this field uniformity, I need to achieve 10 volt per meter. So therefore, I need to ensure, okay, I actually will measure all the 16 point. I will have all the 16 point, all the forward power as shown over here. So next, okay, I need to arrange the highest forward power. For this case here, you can see that the highest will be 40. So the highest to the lowest, as you can see from here. So I arrange from the highest to the lowest. So next, if you still remember, I need to do a minus 6. Can you still remember? Subtract 6. So I do this 14 minus by 6, okay, which is 34. So basically from here you can see that this 1, 2, 3, 4, 5 will be able to achieve the range. However, okay, 5 out of 16 is actually 31.25. So I'm not able to meet the criteria. So next I actually fall onto the second one. So if you still remember the flow chart, I can't make it. So next I find the next highest, which is 37. Again, I minus 6, so will be 31 over here. So from here to here, I actually have 8 out of 16, which is 50%. Okay, this cannot meet my criteria of 75%. Again, okay, I will move on to the next one, which is 35. So 35 minus 6 will be 29. So over here, you can see that I'm actually able to achieve 12 out of 16. Okay, so therefore, I will be able to achieve this 75%. So basically, once I'm able to achieve this 75%, I actually quantified that I will be able to achieve the field uniformity. So basically, this is the analyze of field uniformity. Okay, we need to achieve 75%. Okay, so firstly, I do a quick one. So firstly, I measure the forward power. Okay, how much forward power I need in order to achieve 10 volt per meter. Okay, for example, for this test, I actually do it at 80 megahertz. So once I done this, I arrange the power from the biggest forward power to the lowest power. So after that, I use the first one, I minus 6. So it will be 34. So over here, I calculate it will be 5. So 5 cannot meet the 75%. So after that, I will use another next highest, which is 37. Again, I minus 6 will be 31. Again, I calculate this is just 8. So cannot meet the field uniformity. So next, I will go to the next highest, which is 35. And 35 minus 6 will be 29. And from here, I calculate, hey, it's just nice 75%. So from here, I conclude that the forward power of 35 dBm will be used. Okay, so basically from the position 11. Okay, so basically this is so-called how we actually do this field uniformity. Next, okay, on step number 8, okay, so once we have find all the forward power, we need to check for linearity or saturation. Okay, remember the amplifier may be saturated, and this is something that we need to prevent. Okay, so once the forward power number are known, the linearity of the amplifier must be evaluated. Okay, for each frequency step, apply the forward power obtained during calibration. Okay, record this forward power. Okay, so after that, we will decrease the output of the signal generator by 5.1 dB. Okay, so next we record the new forward power applied to the antenna. Subtract the new forward power from the original forward power. We need to verify that the difference is 3.1 and 5.1 dB. Okay, so basically, if we are able to so-called control the signal basically by reduce the output power from the signal generator, we know that the amplifier is not saturated, and therefore we know that the linearity we will pass, which means that we actually prevent the amplifier to go into the saturation region. Okay, so this will be step number 8. Step number 9, okay, we need to adjust the setup if necessary. So if the field is not uniform, okay, we need to adjust, for example, the antenna placement. Okay, so we need to adjust the antenna height, distance from the test area. For example, we can bring it closer slightly. Okay, not really need to comply under this 3 meter. We can move it slightly towards the antenna. Okay, we also can determine the power level, the chamber configuration. Okay, so if let's say whether we need to put additional absorber so as to ensure that we are able to achieve the field uniformity. Okay, so with this, I'd like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.